All right, so chapter 4, increasing and decreasing intervals, is chapter 4.1. Pretty easy section. Let's get right to it. We're just trying to find out where functions are increasing and decreasing. And the way we do that is by analyzing the first derivative. So let's take a look at this parabola right here. I'm just going to make a statement here. For a function that is continuous and differentiable on an interval I, so on any interval I, it could be negative infinity to infinity or 1 to 5, whatever it is, the function f at x, this, is increasing if the first derivative is greater than 0. So increasing. Increasing is where the slope of the tangent, so if I put a tangent here, this slope is positive. If I put a tangent here, this slope is positive. If I put a tangent here, this slope is 0. So we can see that the function's increasing on this side because all the slopes of all the tangents are positive, which means the first derivative here is positive. So if I split this parabola in two, on this side I can say, well, f prime at x must be greater than 0 on this side of the function. Whereas on this side, every slope is negative. All these slopes are negative here of the tangents. So we can conclude that this side, f prime at x, is less than 0. And that's what this is saying here. F at x is increasing if f prime at x is greater than 0, and f at x is decreasing if f prime at x is less than 0. You find your first derivative. If it's less than 0, the original function is decreasing. If it's greater than 0, the original function is increasing. And if it's 0, we already know this one from chapter 2 and 3, this is when f prime at x equals 0. Okay, it's pretty straightforward. I mean, we already know the f prime at x is 0. Now we're going to start determining the greater than or less than. So working with inequalities is a little bit different. I have a cool trick to work with inequalities, so we'll see that on in the next question. Let's take a look at this question for now, though. Let's consider this graph. This is the first derivative of f at x. So if the first derivative is positive, this is where it's positive up here. It means that the original function, if I have to graph f at x, is increasing. So I know that from negative infinity to this point, my function is increasing. So I could be going up, increasing, 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 and then it's 0. So I have a turning point. Doesn't matter where this point is. I could have gone up here, I could have gone here. As long as the function is increasing and then goes now to decreasing, and it's going to be decreasing all the way to this point because this is my next turning point where the first derivative is 0. Remember, this is the first derivative. It is positive up here, which means my original function has to be increasing only in those intervals. So I can go decreasing now, decreasing, decreasing, and now I have to start increasing again because this matches this point. Again, this is just a potential graph. I just made this up. It could have been anywhere. But as long as the interval between these 2 points on the original function is decreasing from left to right and increasing where it's positive, this is correct. Okay, so pretty easy thing to understand. It might get a little trickier when we get into some questions where we have to solve for the inequalities, but we'll see that next. Okay, so over here we have to determine whether each function, or when each function rather, is increasing or decreasing. So we know that this function kind of looks like this, right? Okay, we know the leading coefficient is an x to the 3. The end behavior kind of looks like this, but we don't know where it's increasing and where it's decreasing. We're not too sure about that. Let me just get rid of this. So we can actually find out exactly where those turning points are by setting the first derivative equal to 0. So the first thing I'm going to do, I'm going to find y prime. I found y prime. I'm going to set it equal to 0. I always have to find the 0. I'm going to factor out of 3x. And now I know that x equals 0 and x equals negative 2. Now, I don't like doing decision tables. A lot of people do decision tables. It's kind of a waste of time. If you know where the zeros are in the first derivative, you can actually just graph it. You know, like I can just do this. And if you understand the graph of a first derivative, there's not much else you need to do. So I can graph 0 and negative 2. This is, look at the first derivative. It's a parabola opening up that goes through 0 and negative 2. Okay. Here it is. It's a parabola opening up. None of these points matter except the negative 2 and 0 because those are the actual zeros of the first derivative. So this tells me, looking at the first derivative, check this out. When is this increasing? It's increasing when the first derivative is greater than 0. So easily visible there. Decision table, this, that, all these testing points, get out of here. Just look at this graph. So now I can conclude, therefore, y is increasing between negative infinity and negative 2, right? And 0 to infinity. Y is decreasing between negative 2 and 0 because the first derivative is below the x-axis. It's negative. So I love graphing the first derivative. It tells me a lot. Even when we get into graphing the second derivative, the information given in a crappy little graph is astronomical. Let's take a look at this one now. A little more complicated. We got to do quotient rule, but that's not a big deal. We know how to do that. Chapter 2, we're pros. Chapter 3 as well. So we're going to say y prime is the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. When I'm solving in chapter 4, I always simplify and I always make sure that my numerator is fully simplified so I can see some zeros. So this is going to be 1 minus x squared over x squared plus 1 squared. No, these don't cancel out. I can't rearrange them and cancel out. They're not exactly the same, so stop thinking that. Okay, so I have my first derivative. I mean, I could have set it equal to 0 before. So if I set it equal to 0, I'm only looking for the numerator here. I don't care about the denominator. Those are asymptotes. The zeros are going to be up top. So 1 minus x squared is equal to 0. That means x squared is equal to 1. And that means, yes, x equals 1. Wrong. Plus or minus 1. Don't make that mistake. Okay, the square root of 1 is not 1. It is plus or minus 1. Now, take a look. Here's my graph. Crappy little graph. 1, negative 1. Opposites, whatever. Here's my first derivative. You can even take a look at this. This is a parabola that opens down. Here it is. That's it. Look how easy it is from here. When is it increasing and decreasing? It's obviously increasing when the first derivative is greater than 0. So I can say y, therefore, y is increasing between negative 1 and 1 and decreasing negative infinity to negative 1 and 1 to infinity. And that's it. This is so easy. There's no reason to make a decision table, honestly, ever. No matter how deep this gets, you can always do this graph. I'll show you when we get there. But do not discount a crappy little graph like this. So much information is just visual right here.